All right. Good afternoon, everyone. I welcome you once again to today's class on machine learning for computational linguistics. I hope you are all having a great day today. Uh,
Good afternoon. Thank you for
Good
having us.
afternoon, Heritage. You're welcome. Vivian Ezejiro Lowu. Vivian, you were not in the last class.
Yeah.
Hope
Yeah,
that
I was on transit. I couldn't join. By the time I joined by 5:31 to 6, I could not get anything. I just said I shouldn't worry. I shouldn't bother about it.
okay, that's
I'll
fine.
watch it later. Yeah.
That's fine. Mercy, were you in the last class? Although we were like, I know Ezeji was in the last class. Okay, so let's kickstart today's class. So last class, we discussed on word embeddings. Who can remind us what embeddings is all about? What embeddings are neural language models. So we discussed what embeddings, why do we need to know what embeddings, and we gave examples. I think Ms. Oni did a very good justice to that by explaining with practical examples on what embeddings are like. Who wants to give us a summary? What did you understand from the last class?
Hi, Kafayat. I think I was in this class. It is on Tuesday. I was not in class. I think that we talked about, though
Okay.
I was up and down, but I can remember we talked about three different types. There's one that uses two words, right? So
Yes.
where she gives sequence of words that we have to check if these two words can occur in the same place. I can't remember their title now.
Yeah.
And
Yeah.
there's the other one that is free, right?
Yes.
And then there's the first one. I know that she gave three examples though, but I'm
Yes.
very familiar with the second and the third one where she said we're also going to give them weighted value, right? Each word, and then we'll
Yes.
compare them. Yeah.
I'd like
Okay.
to also add that if I remember correctly, we gave us the definition as just simply put, turning words into numbers so
Okay.
that the computer can learn it. And I
Yeah.
think this is, yeah, and that's the essence of this computational linguistics that we are all in, to be able to turn words into numbers. And I think we've also mentioned why we need word embedding, still relates to having to match semantic and syntax, just bringing
Yes.
them together. I think I remember that.
Yes. That's very good. Vivian and Heritage. Thank you very much. That was awesome. So remember the basis of what embeddings is that you are turning the words into numerical vectors. So as your machine learning can transform and then give you the result in whatever aspect you are looking at. So today we'll be moving on to neural networks, the concept and feed-forward architectures. So why do we need to study neural networks? Remember in previous classes, we have discussed few machine learning models that can be used. You can remember the machine learning models we have discussed in this course that can be used when it comes to classification. And we also look at various examples to back them up. So who can give me that?
Base, naive. I've been naive
Yes,
base.
exactly. That's very good. So there is one more that we discussed after naive base. That was
I
very
think that's
recent.
the one. That's the one we've been using regularly. Oh. Naive base.
Yes, aside naive base, we also discussed another model that you can use when it comes to text classification or classification generally. And that was in the specifically they studied the naive base. You are very correct. And the second one was the logistic regression. Yeah. So both of these models can be used for classification when it comes to linguistic research. So do you want to give us the examples of classification tasks? I think by now we all know more than one or two examples when it comes to classification. A good example is when it comes to classifying whether a mail or a message is a spam or not. Remember. Now, neural network is another machine learning model that can be used for classification when it comes to linguistic research. And what do we mean by neural network? Is a computer system inspired by the way the human brain works, by learning data, and by adjusting connections between units. These units are called neurons. Neurons. Um, if you remember clearly, the procedure for the machine learning models we've discussed so far, they rely on mathematical formulas. How? The naive Bayes, take for example, let's say we want to classify a mail as either spam or not using the Bayes approach. The normal procedure, if you remember, is that he counts the number of selected features. By features, we mean can be words in a text or the likes that appears in each of these category. Selected features can be, let's say, congratulations, you have won. By then, you know they have scammed, they are scamming already. Or let's say, hooray. Hooray can be another selected features to say that, oh, this mail already is not something that can be relied on, it's a scam. So then, after then, the Bayes then use Bayes theorem. Remember, we discussed Bayes theorem as well to calculate the probabilities, and then the text will be classified as a category. That's selecting the one with the highest probability. And as for the logistic regression, we did that recently. We calculate the weighted sum of the features, right? And then use the sigmoid function to convert it to a probability. So I'm not sure. I hope there's a sound here on that, and I hope it's not disturbing. Let me try to. Yeah, sorry for that interruption. So, well, what we are trying to say in essence is that these two approaches we have discussed earlier, the two models, they both rely on mathematical formulas. And how is neural network different from these two? Like we said earlier, neural network is a computer system. It's a powerful method as well for classifying text and NLP in natural language processing. And how it is different is that, first, it does not rely on mathematical formulas, unlike the Bayes and the logistic regression. Neural network use layers to transform and interpret, and that's how it works. A basic neural network has three types of layers. We have the input, the hidden layers, and the output layer. Let me give a clear picture of how this neural network looks like. I think I'll have to share another screen. Just give me a minute for my screen to come up. But are you with me? Do you have any question before we go forward? Hello? Am I communicating, please?
Yes, you are. No question.
All right, so I'll be sharing another screen of so as for us to understand better how neural networks looks like. Okay. All right, so kindly confirm you can see my new screen on where we have input layer, hidden layer, and output layer.
Yes, I can.
Right. So this is how a neural network looks like. Like we mentioned earlier, a neural network has three layers: the input, which takes in the data, the hidden layer, and then the output layer. So this input layer, you can see the circles on the left, the X1, S2, and then S3. They receive the data, and each of those circles represents the data. It might be a word, let's we call it features, right? Either a word from a text, or mostly in linguistic research, you deal with text. Yes. So they call it features. Those are the X1, S2, and the S3. And a good example is the word embeddings that we treated in the last class. This is a perfect illustration, because what happens in the first layer of neural network is that you feed in the data, and this layer's job is to convert each of those data or each of those words. Let's say, for example, boy, girl, woman. Each of these words will be converted into a numeric vector, right? That's what we did the word embeddings. You convert it to a numeric vector that reflects the meaning of those words and then their relationship to each other, right? So, unlike in traditional text data, what they are just strings, and you can't process them mathematically. And that's necessary for you that you convert them to numerical data. So that's why we have a perfect illustration using the word embeddings. Now, if you look at these lines, these circles here, we can call them nodes. Remember when we were doing, okay, so that was for PGM class. So you call them nodes, or you call them neurons. Nodes or neurons, but for the sake of this class, let's use neurons. So each neurons in one of these layers is connected. This is a neuron, X1, is connected to another neuron in the hidden layer, right? S2 is connected to another, so they are connected to all the neurons in another layer. And these lines that are used in connection, these are called the connections. Okay. See these circles here? We call them neurons. And these lines, they are called connections. Call them connections, yes. They are the lines linking one neurons to another. And each connections in this network has a weight attached to it. The weights determine the influence, just like when we did the regression model, we say the weights of each of those features determine the influence that particular feature is having on the output, right? So the weight in each of these cases now, each lines it carries the weight, which determine the influence that one neuron, say X1, acts on another neuron in the hidden layer, say H1. And when you are training your data using software, these weights are determined automatically, so you don't have to bother about that. All right, so in the hidden layer, you can see what happens in the hidden layer is that each of these layer process whatever is received from the input layer and then transform them to learn the information. Do you get that? It's like you transforming the information received from the input layer so as for it to learn the pattern or relationship between the words or between the features. And then from the hidden layer, you transform to the output layer. What happens in the output layer is that all this transformed knowledge are then used to produce a result or an output. Now, this result is the classification result we are looking for. It's like deciding whether a text belongs to one category or another. So in summary, as the data moves from the input layer, which is this, to the output layer via the hidden layer. The data cannot get to the output layer without passing through the hidden layer. The network, in that process, the network learns the meaning of the words to then transform the knowledge and then give a result. The result in this case is the output. That is the Y in this case. So do you have any question before we move to the next one?
Hi Kafaya. So it's just one output we are getting from multiple string of words.
Yes, it's just one output to say whether the text is classified as yes or no, spam or not. It's just one output. And that output, mind you, is a probability value. That is your Y. Remember when we talk about logistic regression, you calculate the weighted sum. You then use the sigmoid function to calculate the probability. That probability, which is Y, we then determine whether a text is classified as spam or not. Remember, it is now based on if your Y is less than a particular value or greater than a particular value. And that is the decision rule. Is that clear, Vivian?
Yes, it is.
All right. So this illustration that we just gave, in neural networks, there are so many architectures that you can use to achieve your output. And one of it is the feed-forward neural network. Others are the RNN. They are not going there. The transformers. We are not going there for the first for the sake of this class. But the feed-forward is one of the fundamental or the foundation of neural network. Whereby there are type of is what we have just illustrated here. There are types of neural network where the information travels in a single direction. There are no diversions. You go from the input to the hidden and then to the output with interconnected nodes, neurons, and connections. So that's what the feed-forward neural network is all about. The key features here is that the data flow in a single direction, it moves forward without looping back. Unlike if we, I think, okay, if your own leisure time, you should look for examples of recurrent neural networks here and the transformers so that you can get a clear picture of why feed-forward neural network is different from these two. So those are the features. And also the layers consist of the input, the hidden, and then the output, unlike others. You don't have this kind of architectures, you know. So that's where I'll be stopping on this part and leave the rest for Miss Oni to handle. Do you have any question at this point?
I'm good.
Fine, thank you. So, Miss Oni, are you there? Thank you.
Oh, sorry, I'm here. Good evening once again, everybody. Okay, so today we are going to continue with what Mrs. Kapayat had started with us. And I'm supposed to start from 6.4. That's the activation functions. Then down. All right. So she has explained how neural network architecture is, and she has given us the background of how, like, what it is about. So in neural network, we have different kind of activation functions, but the common ones are the three that are mentioned here. We have more than these three. We have the TAN-H, we have the sigmoid, we have the ReLU, we have the LU, we have the leaky ReLU, we have the softmax, and then we have another one I can't really remember. But these three are the common ones. I have to mention the others just in case you later come across them. So now, what do they do? These activation functions, what do they do? So the activation function apply a nonlinear transformation and decide whether a neuron should be activated or not. Like from what Mrs. Kafaya had explained to us, she mentioned that the way neural network works, it works like the human brain with so many neurons. So what the activation function is going to be doing for you is it will apply a non-linear transformation. These ReLU, sigmoid, softmax, and the other ones I've mentioned, they are non-linear transformation. And then after applying them, it will now help to decide if a particular neuron, just imagine a neuron in your brain, should be activated or not. For example, now, just a layman example. Maybe you have to eat a pie or drink a milk or yogurt now, and as you're about to place it in your mouth, you actually tend to perceive the scent or the odor. So now let's assume that you're about to put it in your mouth, and then you perceive the aroma, and it's so nice. Your nerves, your neuron tells you, yes, it's safe for drinking. But if it is the other way around, and as you're about to place it in your mouth, it gives you this sour, conk, very bad odor. By default, your brain tells you that no, this is not to be taken. So that's like what we are trying to do here. We are trying to make a computer, we're trying to build our algorithm such that after so many layers, okay, after this, then you move to this, and then you move to that. After so many of such, should the neuron at the end of the day be activated? That's the output. Should it be activated or not? And that's what brings us to the activation functions. We have different activation functions, and they all have, where they are good at, the data set that they are good at, and the ones that, if you are faced with this kind of data set, you might not want to use this activation function. If you are faced with this one, you might want to use this one. So that's the three. So let me put on my whiteboard, see if I can write a few formulas. Okay, so let me start from the sigmoid function. Let's start from the sigmoid function. Okay, so we have mentioned sigmoid function in this class before. Can anybody remind me where? We have mentioned it in this class before. Maybe when I'm done writing the equation, maybe we'll remember. +1 plus exponential minus x. Can we remember now? Is this formula a bit familiar?
Yeah, that's
Regression.
logistic regression also. We did it last week.
We did it 2 weeks. Regression.
Yes, we mentioned it in the logistic regression. Yes, and don't forget that it was even the same name, the sigmoid function, and there is a bit of closeness actually to it. Just like in logistic regression that we talked about, the sigmoid function also helps in binary classification. If you would remember the logistic regression that we did as well, this segment function is used in the last layer for binary classification problems. So it's when you use it when you have maybe a yes or no. If you are trying to predict a yes or a no, or you are trying to predict spam or no spam, or you are trying to predict positive sentiment or negative sentiment, that's when you can use it. And that's also the situation where you can use your logistic regression. So actually the segment function, the equation here, is what will make your logistic regression work. So don't try to remove it and say neural network segment function, logistic regression segment function. No, segment function is a segment function. So, and okay, let me not go to this. I was going to say that it has a way of squeezing your numbers into 0 and 1. But I think I'm going to draw a graph to illustrate that if we would understand. I think we'll draw a graph. So we also have to understand that the segment function is the formula, the mathematical representation of logistic. That's what makes logistic regression. And then logistic regression applies a non-linear model, and it passes it through a segment function to get the probabilities. So without segment function, logistic regression will just be a linear regression, and it will predict outside of 0 and 1. It will predict outside of a binary form of classification. So the segment function is the same. The one you have learned before is the same as this segment function. But in the case of neural network, it is one of the activation function. So how does it work? Sometimes you can see, they call segment function an S-shaped curve. They call it an S-shaped curve. And because it gives something like this, at the end of the day, if you try to plot the graph for it, it gives you something like, let's assume this is 1. Assume this is, of course, you know that this center here is 0. Then this is 1. Sorry for the diagram. My hand is not straight. This is 1. This is -2. Assuming this is 2. At the end of the day, segment function will give you a shape like this. Please pardon my, something like this, such that no matter how negative your x is, no matter, even if it is -100, your output will still be 0. That's, you will see, this is your x. Oh, how I wish we would understand how plotting a graph works. This is 0 here in your x-axis. This is your y-axis. This straight one here, this line here is your y-axis. And then this other one here is your, I think the horizontal is your x-axis. So no matter the output, when your x, your x is 100, your y will still be 0. It will be here. And then you can trace it. When your x is -2, your y is still 0. Up until at this point where you can now start noticing few changes. When it is 0, pardon my diagram. When it becomes 0 here, then your y should be 0.5. And going forward here, whatever you get here, no matter how positive it is, it will squeeze your output to be 1. That is why you use it for prediction of binary classification. It's always between 0 and 1. It's always between 0 and 1. spam and not spam, positive or negative, yes or no, boy or girl. Are you predicting if this image is a cat or a dog? That's what you can, those are the kind of data set that you can use the sigmoid function for. And take note that the more positive your neuron is at, the more positive you have, like the more positive here, the more you have the tendency for your neuron to be activated, because it is tending towards 1. So if it's tending towards 1 here, then your neuron is activated. If it's tending towards 0, then your neuron is not activated. That is what makes it, sigmoid function. So it is related to logistic regression. Please, let's put that one in mind. Another example is by trying to predict if a particular fruit is an apple or an orange. If a particular fruit is an apple or an orange. So you know that whenever you have this greater than 0.5, your point here, when it's greater than 0.5, then you know, oh, it's an apple. When it's less than 0.5, you know it's an orange. It can't sit in between. It can't sit in between. That's a sigmoid function. Then the other one that is common is the ReLU.
Hi,
Is
honey.
the ReLU.
Hi,
Okay, go ahead.
I will take you back a bit. Are we using
Okay.
this sigmoid function to wait? Let me rephrase the question. So the neuron
Okay.
uses the sigmoid function to get activated. Is that it? So is the calculation from the sigmoid function that either activates the neuron or not?
It is the output. The neuron. Okay, let me draw this. So, like the diagram that Mrs. Kafaya showed us at that time, let's assume we have our input layer here, and then we have hidden layers here. Let's not forget that our hidden layer can be more than 1 layer. At the moment, this is just one. We can have another one like this. We can have another one like this before we now get to the output. For sigmoid function, it will be 2. So it's either is this or is that. So at the end of the day, we have our weights. Okay. So we have them being interconnected. At least you have an idea of how it should look like in the one that Mrs. Kafaya showed us at that time. So pardon my diagram. So you have them connected like this. Same thing goes to these ones. Same thing goes here. Then you have these ones too. So you have them connected like that. That's exact way our brains two are connected. That's the exact way our brains two are connected. Now, the activation function is like inside of this hidden layer. So we have the input layer, which is like, you know, like our data set now. The input layer passes through this hidden layer, in which this hidden layer would have one activation function. If it does not have any activation function, then what you are doing is a linear regression, a normal linear regression. It is activation functions that makes it non-linear, because there are sometimes that our classification goes beyond linear regression, goes beyond linear classification. It has to be non-linear for you to be able to correctly categorize whatever you are trying to categorize. So the activation is like inside of this neuron, inside of these neurons here, or sometimes they call it nodes, inside of it. So it is now, your activation inside it can now be a sigmoid, or it can be ReLU, or it can be softmax, anyone. It is now after your input has passes through this that you can now make a correct prediction. I wish we understand. The truth of matter is that you can't really use ant to calculate
Sorry.
neural network. Okay, go ahead.
So you're saying that what it's like a guesswork. So if I have data, just dump it in, right? And the what do you call these things? Inputs, hidden, outputs.
Yes, this is
What neural
input.
network?
Yes,
That's the name for it. It's called a neural network.
yes, the whole architecture is called a neural network.
Neural network. Good, very good. So you're saying that, or from what you have said, I understand that this entire architecture, for me to get to output, I would run a sigmoid function with data. I would run a ReLU, and then I'll run a softmax. And so that will now determine what my data is supposed to use or become. What's the rule?
Okay, no, that's not exactly what I'm saying. What I'm saying is that we have different. Okay, how I wish in your quantitative class you have gotten to t-test or ANOVA or regression or chi-square. Your kind of data set will actually determine the kind of activation function you are opting for.
Not the other way around.
What do you say?
Not the other way around.
No, not the other way around. By the time you understand these activation functions, you will know if you are trying to predict a binary output, then you might want to opt for a sigmoid function activation function. Do you understand? So that you having the theoretical knowledge, and that's what we are providing. Don't forget that you are going to actually be using softwares for these things. And you know, life is now simple. Even on your R or your Python, you just have to type the name, just ReLU or sigmoid, and it gives you whatever you are supposed to get. But you having the understanding of how it actually works makes you a professional. And then when you see a data set, you can easily say, oh no, this one actually sigmoid will work better for this. And even if you have a data set and you decide, maybe you are still trying to juggle between understanding it, and you decide to use the three common ones, or even more than the three common ones, you would also see your output, and you'll be able to determine, oh, this activation function works better for this data set. By the time you also see the kind of output you're having.
Right.
Okay. All right. So another activation function that we'll talk about is the ReLU, which is ReLU is rectified linear units. Rectified linear units. Rectified linear units is written as ReLU. Okay, so for the ReLU, this is the function. You know, from theory, it's very easy, because it is not even as, like, even the function is not as keen or as confusing as the sigmoid. So you have your f of x is the max of 0 or your x. So it is generally known that when you're not even sure of the activation function to use, you can just use your ReLU. And I'm going to explain more. Now, the way your ReLU graph looks like, don't forget that I told us that the sigmoid gives you like an S shape. But this time around, this ReLU gives you something like this. Of course, this is your f of x. Then this is your x. This is your x, you know. Then this is your negative. Let's say negative 3. Then this is your negative 1. Then this is your positive. This is your 2. Something like that. So it gives you, is either a 0 or your x. So it's either a 0 or your x. So for whenever your x is less than 0, that's when it's negative. Your function becomes 0. But whenever your x is positive, when it's greater than 0, it gives you back your x. And what it means is that the literal meaning of rectified linear unit, or literal conclusion that you can understand, is that the more positive the neuron is, then the more activated it is. The more positive the neuron you are calculating is, the more activated it is. And also another beautiful thing that ReLU has as compared to sigmoid is that it overcomes the vanishing gradient problem. For example, in this one, there is a vanishing gradient problem. And what's gradient? Gradient is like the change, change which is represented by delta. Maybe the change in x or the change in a, where you want to check the before. Is it the before minus the after now? But at this point here, there isn't any gradient problem. It has squeezed it to be 1. And same thing goes here. The only little change you would notice is just in this angle. So that's why there is a vanishing gradient problem for sigmoid function. And it now limits that function to be used for binary classification. But for ReLU, there is no vanishing gradient problem here. It keeps going and is not constraining your maximum. It's not constraining your maximum. So your ReLU overcomes the vanishing gradient problem. And that's why it's generally known that it's like the most common activation function, and that when you're not sure of which activation function to use, you can just try ReLU because you are likely to get something good out of ReLU. Then for the softmax, that's the third one in our material. For the softmax, it is used for multi-class problem. The softmax is used for multi-class problem, and I wouldn't really know how to make us understand this, but the formula, even though I know that the formula is a bit more technical than the other one, so still have to study it. The softmax formula exponential yi divided by summation of exponential yi. Okay, so that's the formula for the softmax activation function.
I'm sorry, very quickly.
Okay.
Softmax used for solving multi-class problems. Is it possible that the multi-class problems are embedded in the input, in, and out?
No.
No.
It's like for multi-class classification, when you are classifying more than the binary that we talked about. Remember we
Number.
talked about binary. So when you have so much to classify,
Right.
and then when you have, I mentioned that when we have more than one hidden layer, that we can have more than one hidden layer. So when you have something that complex, you have 2 hidden layers, 3 hidden layers, and they are all connected to themselves. Let me see if I can see a picture online of, okay, something like this. So in that case, you can just, switch to, okay, let's see this picture. So in this picture here now, you can see that you have more than one. This is one hidden layer. This is another hidden layer. However, at the end of the day, we are predicting just binary classification. But let's assume you are predicting more than this with so many hidden layers and they are connected. That's what we call multi-class problems, or I can also say multi-class classification. So for softmax, it transforms what your output should be. It transforms it into probability distribution. So that's the strength that softmax has. It transforms it into probability, and then you'll be having numerical figures when it gets to softmax. But personally, to me, I feel like amongst the three, softmax is used for a really, kind of complicated neural architecture. So I hope you understand that. So let's go back to our material. Okay, so we have the ReLU first here. Then we can see it works fast and works well for hidden layers. Then the sigmoid squashes outputs between 0 and 1. It's good for binary classification. I think I've mentioned that. So then softmax is used for multi-class problem. Okay, then the next concept that we have is the back propagation. The back propagation, and back propagation is the process of adjusting the weight in the network based on error. How does the back propagation works? For example, now let's assume there is a sentence that I want you to classify, or there are a set of sentences that I want you to classify as maybe positive or negative. And let's assume I have 5 of those sentences. And how many are you in the class? You have 1, 2, 3, 4, 5. Okay, you have 5. So let's assume each of you are connected to yourself. Maybe Vivian is connected to Wura, and Wura is connected to Messi. Messi is connected to Kende and Wura. Like, you are interconnected like that. So now I give you the first sentence to classify. Vivian thinks of it and say, oh, based on this, I think this word means it's going to be negative, and passes it on to Wuraola. And Wuraola is added from Vivian's standpoint. Wuraola added our own view to it, passes it on to the next neuron, and that one also, from the knowledge of the connecting ones, add his or her own to it and pass it on. And at the end of the day, they make the final response and tell me, oh, it's positive. Then if it's positive, if it's actually positive, then they are correct. If it's negative, they are wrong. And then they sit back and then like, oh, where did we get it wrong? And then they go back again. Like, back propagation focuses on the error. It goes back to the error and then use the error that it has made to how do I put this in English now, to make better the next prediction. I don't know if we are kind of getting the point. So it's expected that at the 5th trial, the class should now have understood the sentiment. I think a similar example was what we did in the quantitative class, where we were trying to check which one was type 1 error and type 2 error. Okay, fine, not the very good example because I didn't ask us to discuss it in internal. But when we first started, the first person mentioned it, I think that was the book, said it was, I think, type 2 error. I said no, it was type 1 error. I explained. The next question, the person said it was type 1 error. I said no again. I explained. Then the third one, I think somebody got it right. The fourth one, somebody also got it right, if I can remember very well. So that's like it. You measured on that error that you made, and then you try to assimilate and say, oh, this was where I got it from. Then let me make another. Let me try again. So that's back propagation. That's like a short name for backward propagation. So what these are the steps. It makes a prediction, then it compares it with the true value and say, oh, so the prediction I made, comparing it with my true value, am I correct or not? So if I'm correct, there is a loss function formula. And if you are correct, you calculate. If you are wrong, rather, you calculate the error. Then you use it to adjust your weight to reduce the error next time. The weight here are the lines. Okay. The weight here are the lines that were connecting the layers. Those lines that were connecting the layers are called the weight. So it will now go back to adjust each of the weight for the next set of prediction. Backward propagation is quick, is versatile, and it has no extra mathematical function apart from the loss function you can use to calculate the error, in which you can do computationally. So, and for backward propagation, you can use it in speech recognition. You can use it to perfect your prediction of speeches. You can use it in text recognition or character recognition, even signature recognition, face recognition. In NLP generally, backward propagation is widely applicable. In every field where you can find NLP, backward propagation is widely applicable. Okay, then the next section is the example. Okay, I think actually I've mentioned the example, the sentiment classification. So a feed-forward neural network for sentiment analysis might use word embedding as input. And thank God that we had treated word embeddings last week. We treated word embeddings, so I think by now we understand what we are talking about. So that could be our input. And then you process them through hidden layer. Through the hidden layer, what you are using to process them are the activation function. So it could be if you are trying to predict if those words, after using word embedding and using them as your input, then you process them through hidden layers. I've mentioned it that it means that it is passing through an activation function. Then if it's passing through an activation function, then we are expected to now be able to predict that based on this activation function and based on it, then our output is positive or negative. So if we are going to be predicting positive or negative, we are likely going to be using a sigmoid function because it is best used for binary classification. It's used for binary classification. So that's if it's sentiment. But if we have a more complex kind of data set, we have more than one or two hidden layer, and we have more outputs that we want to classify, and that is more than two, we might move to softmax and then check it before we can now say, okay, this activation function works better for this kind of data set. All right, so okay, I think another question that might be in our heart is that, so how do we now check it? There is something that we call training set and test set. I don't know if we've mentioned it in the class before. When you have your data set, anytime you're even dealing with machine learning or data science, you split your data into 2 or 3. But I think most times it's true to have training set or test set. Your training set could be maybe 70% of your data set or 80%, and your test set could be 20 or 30%, as the case may be. Then after you have trained it, right? After you have trained your data, let's assume you use the sigmoid function to train that neural network now, and then you have supposed predictions. You can now compare it with your test set and then see if it works well. Or you can use another activation function and then you compare it with your test set. If it works better, then that will now tell you the kind of activation function that works for your for that data set. So the strength and weakness of neural network, we have that the strength is that it can learn complex patterns in large text data. Yes, I think that one is quite obvious. When we are dealing with something complex, it can quickly learn. We can train it for a complex kind of data set, and it works well with word embeddings. Yes, we mostly use it when we want to, in linguistic, we use it for word embeddings a lot. But for the weakness, it needs a lot of data to train well. It means that you need to have a wide number of data. The naive Bayes, we could even use it on just maybe 20, 30 data sets. But when we are dealing with neural network, for us to be able to train our model well, we need a lot of data to be able to train it well. And it takes longer to train than a simple model. Definitely, you can see what is attached or what is associated to a neural network. So it needs a lot of time and data for you to be able to have something good. So if you do not have enough data, you might not opt for neural network. And if you don't have enough time to train your data, you know the data is already much in the first place. If you don't have enough time to train your data, then you might not want to opt for neural network. You can think of another tool, maybe Logistic, maybe naive Bayes, like we talked about, depending on your kind of data set. Okay, so do we have any question before I give it back to Mrs. Kafaya for the R? Okay, sorry, for the practical exercise. Okay, I think there are no questions.
I'm good.
Okay, I think there are no questions. Now, Mrs. Kafaya, please go ahead.
Okay, thank you, Miss Honey. So we move straight forward to the practical questions. Let me share my screen again.
I'm sorry. Did you say we would move on to the
Practical exercises.
practical? What happened to our feed forward neural network in R?
In R, that one, I will give it to you as an assignment. You run it on your own. If you have any issues running it, you then come back with the next class and then we can trash it out. Is that clear? Meritage.
It's not clear.
Why
We
is
have
it not
how many
clear?
assignments we have on our neck.
Right now, you should be an
Submit.
R expert.
No,
Isn't it?
I'm not. No, I'm not R expert. So R Ojeki, R
Maybe, okay.
Romi.
Maybe Messi is the R expert in this class then. Or let's say Vivian. Or who is the R expert? So the R code, you let you run it. Practice with it. I say practice makes perfection right. You don't have any problem running it. The codes are there. Try them out. See what we are trying to explain in the practical aspect. And then let's see if you have any problem in the next class so that we can trash it out. It's just for you to practice. Just practice with this. Is that okay?
Okay, I'll take that.
Yeah, I like that. All right, so let's move to the practical exercise. How many of us are in class today? This course, is it an elective?
I don't think so. I think it's a
No, I think
It's
it's
not.
required.
required,
Okay.
yes.
Do you know how many of you are taking this course? And the quantitative distance too. How many of you are
Everyone
right?
was
How many
How
are
many
we?
of how many are you?
Ah, 10
I
now.
think we're
Maybe
around 7 or 8.
7 or 8, yes.
That's
Seven or
minus the
eight?
PhD student. So
Yes. Yes, I get that. So
Minus,
sorry, minus the PhD student rather.
okay, how many PhD students do you have
I'm
that are
fully in the,
taking this course?
I, I'm in this class. I'm activated. I'm really in both the quantitative. Actually, right, we're just supposed to audit and
Okay,
not necessarily. Audit means audit, they actually admitted us based on the
okay,
fact just audit the classes. We are not meant to participate, except the meaning of audit has changed in this minute. We're not supposed to participate in anything. But I need this to, to give me a foundation to my research. So, and that's why I'm present in almost all the classes. I'll participate in the assignments, the tests, and all that, knowing fully well that I don't get a certificate or what's that thing called, a transcript at the end of it. But I'm still trying
okay.
as much as possible to commit to it because it is also for me. For Anfani ara mi, no me.
Then
So please, I'm part of this class.
okay, heritage.
That's
That is a very good one. That's a very good one. I love that. So are you saying that all of you in this class you are supposed to audit this course and the quantitative and not to take the exams? Is that what you're saying?
no.
Wait,
Okay.
Heritage, let me explain to her. Kafayat,
Oh, yes,
we
thank
are
you. Please go.
master's students, right? So in
Yes.
master's class, I think all of us are taking it required, and we are going to write and pass it. And then I think we are about 8, if I'm not counting wrong, give or take. We're not up to 10. Let's just use a round figure 10. Then the
Okay.
PhD students, I think they are 2 or 3. I don't know. So whether they are
That
writing the exams or not, I do not know. But I'm talking
okay.
for master students, give or take round figure 10, but we're not up to 10.
Okay. So the master students are they supposed to just audit the course or they are supposed to take the exams?
We are taking exams. Which one is audit?
Okay, when Heritage was mentioning auditing.
Because he's a PhD student.
Heritage is a
Okay,
PhD student.
okay, Heritage is a PhD student.
Yes,
Yeah.
that's what
Oh, awesome. Now I get it. Now I get it. I understand. Thank you very much for that clarification. All
Okay.
right, so let's move forward to the practical exercise. In your own words, describe what neural network is. I've not heard from Mercy today. Olo Wuraola, I think she just joined again. Ezeji Royal. Mercy, please go ahead with question number 1.
is. You're not sharing your screen.
Okay, sorry. Thank you, ma. Thank you very much, my son. I thought I will share again. My screen is up, but I will share. Mercy, are you there?
Yes.
Okay, so can you see my screen now?
Yeah.
No, not
Fine.
yet.
Yes. Oh, it's not again.
Oh,
Can you
you
see
might
my
have
screen now?
you might have to, I don't know, highlight it again.
Okay. Then there's my screen then. Yeah. Is my screen coming up?
No.
Hello? Oh,
Kafayat, you are sharing, but you're not sharing the tab.
okay, I was there earlier. Yes. Okay, so can you see the questions now?
Yes.
All right.
Yeah.
So Mercy, please go ahead. Question number 1. Describe what neural network is in your own words.
All right. So neural network is a machine learning model that trains a machine learning model that trains that has to do with I don't know, patterning. It has to do with using how the human brain works. Yeah, that uses how the human brain works to train the computer. I
Yeah.
think that's and it has it has 3 layers. You said it has the
Yes.
hidden layer. The
Yeah,
hidden
moving on
layer,
to
right?
question 2. Yes. Go
So
ahead, guys.
the input layer first, then the hidden
Okay.
layer, then
Okay.
the output.
Thank you
So
very
the
much.
okay, thank you.
Yes, go ahead, go ahead.
Oh. So the input layer receives it. The hidden layer processes it using I don't know. You mentioned segment
Receives
function.
what? The hidden layer
The
receives what?
data. The input
Okay.
layer receives the data. The hidden layer transforms the data using the mathematical operations you mentioned. I think that was where you mentioned the segment function and all of those things. Then the output layer is one that now produces the final result, which is usually
Which is usually
a prediction, something.
yeah, Mercy. Thank you very much. Mercy, are you
That's
are
one.
you eating or you are cooking?
Yes, I'm eating.
You are eating. Wow. That's good. Well done.
Thank
Agbadere.
you. Thank you.
So Ezeji Royal. Mercy said neural network is how the human brain works with the computer and all of that. So what is neural network used for exactly? Ezeji, are you there?
Yes, I'm here.
Yes. In addition to number 1, what does neural network do?
I would say that I used to capture complex patterns in tests, and neural network does not rely on mathematical formulas like logistic regression. So, just like she explained, so the way the neural networks captures patterns is through the layers, like the neurons,
Yes.
the
So
input layer, hidden layer, output layers as they are connected. And the input layers, those X1, X2 you explained earlier, they are the neurons. And then the hidden layers are the connections. So,
Ezeji,
yes, ma'am.
yes, thank you very much for that. The
Okay.
input layer, the end of neural network, like I mentioned earlier, what I want to hear you have not mentioned is used for text
Um,
classification, just like the logistic regression and the naive Bayes. You also use neural network to classify text when it comes to linguistic research. And it has 3 layers, like you've mentioned. Each of those layers have their own role. Yes. And an example of text classification that is used, we've used so many examples. There are also natural language processing, remember. So question number 4, I'll give it to Vivian. Vivian, I almost answered the questions.
Why did I feel like you were going to give me the NLP tax question? Eh? Give an example of an NLP tax where feed forward neural network might be useful.
Yes.
Example, feed forward. Is it not the sentiments? We can use it for the sentiments.
Sentiment analysis, yes.
Yes.
One more example. Vivian,
Um, eh?
yes, give us one more example, Vivian.
Is that correct? Let me know. Let me
Yes,
see.
it's correct.
Okay.
It is the an example of a natural language processing task is the sentiment analysis. Yes, you are very correct. You are very correct.
Another one would be, hmm, okay, should I use the same one, spam or no spam, that people always talk about?
Exactly. It's also a classification task. So that's it.
Yeah. Thank you.
That's very correct. So explain what an activation function does. Olowu. Olowu Raola. Are you there? I've not heard your voice today.
It uses activation network to decide whether a neuron should fire or not, for you to work or not.
Can you say that again? Your voice is low. Olowu Raola.
Can you hear me?
Yes, I can hear you now. Raola, we can hear you loud and clear.
Fire or not.
Seems your network is bad.
Activation should fire.
Okay. Hello, Raola, your network is quite bad. Who wants to assist? But I can barely hear what you are saying, but I know
Can you
you
hear
have
me?
the correct answer. Yes, I can hear you now. Go ahead. Okay,
Maybe you just type it also, because our network is bad, I think.
I can see that. Hello, Raola, if you can hear me, type your answer in the chat box. That's a very good one, Vivian. All right, so name two common activation functions and describe where they are used. Maybe Heritage wants to help us with this.
Uh, two common activation functions. The first one would be the sigmoid function. This helps. Same, you've explained that it can also pass off as logistic regression, and that if you have a sigmoid function without an activation, it is simply a linear regression. I want to believe that's how I understood that.
Yeah.
So in order to carry out the sigmoid function, to successfully carry it out, it must go through three layers: the input, which receives data, the hidden layer, which processes data, and the output that produces this data. And the sigmoid function's output would always between 0 and 1, yes or
Yeah.
no, positive or negative. I don't know if male or female also falls
It's
under
also
this
a
category.
classification. What do you
Sorry?
say?
I said I was even going to ask, does male or female also fall under this category?
The category of zeros and one.
Yes.
Yes, it can. It can because you can either classify a gender as male
Mm,
or female.
or
As a
female.
binary. Yes.
How about what's that thing we always say in the math class? True or false or something like that too. Yes?
Yes, exactly.
Yes. Okay, so that's sigmoid function. And
Yeah.
then the ReLU function would work well with hidden. Actually, I think I want the softmax. The softmax function would activate in multi-class problems. This is when you have a lot more maybe data in text format, and then it can handle complicated neural network architecture. This is what
Awesome.
you understand.
Awesome. Awesome. That's very good. Heritage. Thank you for that. So explain how back propagation helps in the neural network link. Vivian. You want to help with
Please,
this?
I want to ask a question before you ask me. So, based off
Yeah.
what Heritage explained, sorry, as sigmoid function, right? So we said that it's basically classifying spam or no spam, true or false. Are we saying that we can only use nominal data for sigmoid function? Is that what we are saying?
That contains binary variables or a classification variable. Is that what you mean?
Please say that again.
Are you saying data that has a categorical variable? Yes or no?
Yes, yes,
Example.
yes.
Yes. But remember when we were discussing logistic regression, we say that the variable can either be a yes or no, that is categorical. And then you use
Yeah.
sigmoid function to convert the weighted sum to a probability to determine the classification of this. Now, whether you have a categorical variable in your data or not, it doesn't tell us if you should use a sigmoid function or not. What tells us whether you should use a sigmoid function or not is the model you are using, in whether the logistic regression, the neural network. You get that? For example, if you're using a regression, ordinary regression analysis, you don't work with sigmoid function. But logistic regression requires that you use a sigmoid function to convert your weighted sum into a probability, just like the neural network. So that's what decides for you whether you use the sigmoid function or not your data.
Oh, I get
So
it now.
your
Yeah. So
data will
it is the model that determines what function to use. Yeah.
exactly, exactly. So now that I've answered your question, you can then go ahead and answer my own question too.
Please, number what?
Number 7.
Explain how back propagation helps in neural network learn. Oh, okay. I think that when Honey explained, I was not paying very good attention, but let me try and recap. So she was saying that it is propagation is thinking backwards. We said that the neural network is like the human brain, right? Where
Yes,
after you feed it information, if it is wrong, it has to rethink or retrace its step to correct those errors that made it wrong. So I feel like it helps the model retrace a step one, note where it has made error two, correct the errors three.
thank you very much, Vivian. That's awesome. So, Olowura, I got your response in the chat box. Yeah, that's very correct. Thank you. Kehinde Oluwayemisi, I think you are just joining. Or were you in class earlier? Okay, she's out again. Is she there? Kehinde Oluyemisi, can you hear me? Okay. Question number 8 is what you are to practice at home and let us know if you have any issues running the how code. Okay, so why do neural network often need more data than simple models? And then what does it mean if your neural network is overfitting and how can you fix it? This will be posted as an assignment on the classroom so that you can submit them. Is that clear? So if you have any question, please do not hesitate to ask. Okay, someone had this up. Vivian, please
Please,
go ahead.
I want to protest. This assignment, they are not too much like this, bye. They are
Yeah.
too much. The assignments are too much. They are too much. Actually, we are doing over 9 courses this semester, and everybody
Oh,
is bumping a loss on us. Every class, every class.
oh,
My body is paining
And
me.
they don't give enough time. Oh. At least if you're giving
ah,
us time for the assignments. Ah.
oh my God. Which one the address was? I can hear
All
the
of them.
voice, heritage voice, a
No,
native
assignment.
voice.
Oh,
Okay.
not jokes. So every class, everybody wants to give an assignment. There's no time to even process what we have.
But this
Mm.
is why they call it master and not BSc. You get that? So don't worry, you'll be fine. Eh? Like I said earlier, when I think Vivian also complained in one class like that. Maybe Miss Oni wants to help while they are giving you, but this is why they call it masters. Don't worry. But I think the assignment, there is no pending assignment on machine learning. Is there any? Is there any pending
We
assignment?
have we
Yes,
have
please.
machine learning and
Yes.
quantitative.
Yeah, I did not even
Please,
For
allow me
you?
any
to.
assignment, give
Yes,
us time, enough time, so that our
Okay.
brain can cool off small before.
yeah,
No,
please.
no problem. That's well understood then. Okay. So just go ahead with the pending assignments and then submit before the deadline. No problem about that.
Yes, looks like we already have two. So maybe if that clears up again, we can take on new ones with another later dates. And I
Okay.
think the spacing too.
All
Yes.
right. Yeah, that is well understood. That's well understood. All right. So I'll leave the floor for Miss Oni to come up again and keep the exercise. Miss Oni, are you there, ma'am?
I'm here. Oh. I'm thinking if we want to go through the multiple choice exercise, and if I were to give it as assignment now, that's another complaint.
No,
Ah,
please let's treat it in class. So we still have some time. Please let's treat it in class, Joe.
Okay,
okay. Miss Oni, do you want
so
to go ahead? Okay. Thank you.
yes, please. Mm.
All right.
Okay, so I'll share my screen and chapter. Okay, please give me a moment, my sister. Okay, I think my system is back. Okay, okay. All right, so just like we used to do, I will just call us, we'll read the question, we'll explain why our answer is which, and then we'll call it a day. So I'm going to start with Eze Jiroya. Question 1. Some of these questions are very easy. Eze Jiroya, are you with us?
Yes, I'm here. Okay, question 1.
Okay, question 1.
What inspired the idea of neural networks? I think the human brain. B.
Correct. Yes, that's very correct. We've mentioned it in the class. Then heritage. Heritage,
Number
let's take
two.
question 2.
Which layer takes in the data? C, the input layer.
Okay, thank you. Question 3. Who is the next? Kende Oluyemisi, were you in the class? I'm not sure. Kende, we can't hear you. Okay.
I think she has
Kende is not audible.
network. She has been going off and on. Network isn't stable, yeah.
Okay. Okay, so Wurola, can you help us with question 3?
Okay, question 3. What does a hidden layer do? B. Learns pattern from the inputs.
It learns pattern from the inputs, correct. Vivian, question 4.
What does fast forward mean? Data moves in one direction only. Feed forward, rather. Sorry.
Feed forward.
Yeah. The answer is B, B,
Okay.
B, B.
Okay, all right. It moves in one direction only. Then back to AZG Royal. Are you here?
Yes, I'm here.
Okay, question 5.
Okay. Which activation function is common for binary classification? You explained that it's sigmoid.
Sigmoid, yes.
Yes.
Very good. Heritage, question 6.
Number 6. Which activation function works well for hidden layers? I would choose softmax, but then I see none. And then I begin to feel like, are they playing with me?
Sorry, you see what?
I see none in C, and I'm like, are they trying to play with
Okay.
me? Because one can get
Okay.
distracted with that.
Yeah, that's what makes it a tough question. So I would also agree with you. Softmax is as compared to ReLU for hidden layers. Yes, softmax is going to be what we should opt for. Then question 7. This is question 7. Okay. Is MC back?
I'm with you. Can you hear me?
Okay. Yes. Is this MC or no?
We are together. Our phone is sort of faulty,
Okay.
so you can't hear what she's saying. So she wants to answer the question with my phone.
Okay. So can they go ahead? Question 7.
Okay. What is back propagation used for? The answer should be adjusting weight to reduce error.
Beautiful. You are very correct. Then Olo will help us with question 8.
Okay. What is one advantage of neural network for NLP? They can learn complex text patterns, I think.
Yes, you can learn complex text pattern. Yeah, that's very correct. Then Vivian, the last question.
What is the limitation of neural network? They need lots of data and computing power.
Yeah, beautiful. Okay, so I'm happy that we are able to get this and we are moving forward. So about the assignment that you complained about, well, one of the things that we should note is that most times for prof course, your continuous assessment are the assignment and your attendance and your interaction in the class. There isn't a special time for CA or all of those things. They are the assignments and your attendance in the class. So they are very, very important. So forgive us if we are loading you with so many assignments. It's so that we can compute your CA.
Oh, I see. We understand
Try to
now.
put in information. Yes. Prof doesn't take extra classes for extra days for CA or all of those things. All right, so is there any questions so that we can call it a day early today? Okay, so if there are no questions, I would like to call it a day on behalf of my colleague and Professor Ubuse. So enjoy your night rest. So we'll see. Oh, I think we have a pending discussion where we said we were going to discuss when the class is large, but still, we still do not have a large class. What do we do?
Oh, that's true. We